Welcome all to this session, which is going to be dedicated for describing curvilinear motion using normal and tangential component. I would like to inform you that this section 12.7 is going to be described in two parts, and this is part number 1. So the objectives are to describe the motion using the normal tangential system, which is abbreviated as T-N, and also we would need to define the radius of curvature, and we will also see that we will have to define the tangential and the centripetal acceleration. Normal tangential system can be used to describe curvilinear motion for many situations. So for example, here we have this sphere moving along a curved path as shown, and if we want to use the normal tangential coordinate system, as we are going to see, we will have to construct two axes. One is called the tangential and the other one is called the normal, and we would need to describe the motion, velocity and acceleration using those two axes. So if a particle moves along a curved path, its motion can be described using a 3-coordinate system. One of them is the rectangular coordinate system, which we already discussed in the previous section. And we can also do it using normal tangential system. And as we are going to describe next, we can also use polar or cylindrical components. Now, the preference is dependent on the nature of the problem. So, if the path along which the particle is moving is known, then we can use the normal and the tangential component to describe the motion. Now, in the normal tangential coordinate system, the origin is located on the particle, and it moves with it. It is not fixed. Now, if we consider two-dimensional planar motion, there are few points to be considered over here. First, as we discussed earlier, at any instant, the origin is located at the particle itself. So if you look over here, this is the origin, just on the particle. The next thing is the tangential axis. So the tangential axis, which is the t-axis, is determined by establishing the tangent at a given point. So at this point, we need to draw the tangent. So this is the tangent to the curve. And what remains is that should the UT point to this direction or that direction along the tangent. And the way to determine this is by looking at the direction where S is increasing. So if we take this point as the origin, we can see that S is increasing in this direction. And this is why we pick this, not this one. This is why UT will point to this direction. Now, once we establish the tangential axis, we draw a perpendicular line to it, which is going to make the normal axis. And again, we will have the same question. If this is the tangent over here, then we can easily establish the normal, which is going to be over here. The question again, should the UN point down or up? And the answer is that UN will always have to point toward the center of the radius of curvature. And this is basically the positive UN, and this is the positive UT. So this is basically what I described earlier in the previous slide about the n-axis, which is the normal axis. So just to remind you, it is perpendicular to the t-axis, and its direction is always toward the center of the curvature, which is O prime. UN is a unit vector in the normal direction, while UT is the unit vector in the tangential direction. Now, if we have a circular motion as shown over here, this is a circle, and this is another one, so the motion is circular, then the radius of curvature is actually the radius of the circle. But what we are going to see next is, what if the curve is a general curve? Then what is the radius of curvature? So if we have a general curve represented by an equation y equals to fx, then the radius of curvature is calculated as follows. Rho, which is the radius of curvature, equals to 1 plus dy over dx squared, all raised to the power 3 over 2, divided by d2y over dx squared, and this has to be positive, and this is why we put the absolute value. Now, let's start characterizing the motion, and we will start with the velocity. Two things we need to know: the direction and the magnitude. For the direction, we know that velocity is always tangent to the path, so it will have a unit vector of ut. While for the magnitude, if we know the path function, which is s as a function of t, then the velocity, the magnitude of the velocity, is going to be ds over dt, which is equal to s dot. So if we want to write the velocity vector, it's going to be v, which is equal to s dot ut. S dot is the velocity, so I can write this one as v equals to v ut, and ut is the unit vector, because we said that this is the velocity vector and this is the ut, the tangent unit vector. Now, as we all know, the acceleration is the time derivative of the velocity. So if we write down the velocity vector, v equals to v magnitude ut unit vector, then the vector of the acceleration is equal to v dot, which is equal to d over dt of v, which is equal to d over dt v ut. Now, you have to be careful here. This is something different. Ut is not constant. If you look over here, when the particle is at this location, so I'm looking at this graph, when the particle at this location, it has ut pointing to this direction, a unit vector at the tangent pointing to this direction. Now, but when the particle moves to this point, as you see, it has a different tangent. And for that, we can't take the derivative only for the magnitude. We have to take the derivative, the time derivative of the magnitude and the time derivative of the direction. And this equation will be v dot ut plus v ut dot. Now, I know you probably haven't seen a derivative for a unit vector, but before I show you how do we do the derivation, let me show you what is exactly the equation that we are going to end up with. the acceleration equation is actually going to be v dot ut plus v square over rho multiplied by un. And I am pretty sure that you are familiar with this equation. This is what we call the tangential component, and this is what we call the normal or the centripetal acceleration. So let's see how are we going to derive this unit vector. Now, to derive the unit vector ut with respect to time, let's consider the situation on this graph. So the particle P was at this position. At this position, we have a tangential axis, and since the motion is moving in this direction, where the s is increasing in this direction, we have this ut, a unit vector. And perpendicular to it, we have un, which is pointing toward the center of the curvature. But after time dt, we ended up with the particle moving to this position, where we have a different ut, which we call ut prime. And if we look at the below diagram over here, we just moved the vector. So this is ut, this is ut, this is ut prime, this is ut prime, and this is the unit vector un. So what we do here, we also call the angle, which measures the difference between this vector and this vector, we call it d theta, which is differential angular displacement. And this one is dut, which is the amount of change in the ut. Now, which is the unit vector, the tangential unit vector. So if we look at the magnitude of ut unit vector, it is basically ut, which is equals to 1. It's a unit vector. Magnitude of a unit vector is always 1. And also, if we sum up vectors in this graph, then we will have ut as a unit vector, ut prime, is equal to ut plus dut. So, to look what we did, we said that this unit vector is equal to this vector plus this. This is how we add vectors. And now, if we look carefully to this dut, if we calculate its magnitude, dut, then it is equal to dut. So this is a vector, this is the magnitude, which is equal to 1 multiplied by d theta. How did I find this? We can find this by using the arc length equation. The arc length equation over here is equal to S equal to r theta. So if you want to find the arc length S, you have to multiply the radius by theta. Using the same analogy over here, du, its magnitude, which is the length, is equal to the radius, and the radius here is the magnitude of ut multiplied by the change in the angle. Now the magnitude of ut is 1, while the angle here is instead of putting theta, we put d theta. So from the previous slide, we found the magnitude of dut which was equal to dut, which is equal to 1 d theta, which is basically d theta. Now, what about if I want to express the unit vector dut? Well, I need a magnitude and I need a direction. For the magnitude, I just calculated it. This is the magnitude of this unit vector. So, its magnitude is d theta. And for that, I'm going to say that this is equals to d theta. But what is the unit vector? What is the direction? So the direction is actually going to be un. So this is the magnitude and this is the direction. Now you may ask the question, why is it un? Well, basically, the assumption here is that for an infinitesimal small change, du has a direction which, if I extend, going to be parallel to un. So if they are parallel instantaneously, then I can say that the unit vector of ut is actually un. And this is why I did this. Now, clearly, if I take the time derivative of this, then I will have dut over dt, which is equal to d theta over dt multiplied by un, which is going to give me ut dot, and this is a vector, is equals to theta dot un. Now, I don't know what is theta dot. So what I'm going to do, I'm going to move to this schematic to try to find the relation, which is between the arc length and the radius of curvature and theta. This is the same equation that I used before, which is S equals to R theta. Now, but I'm writing it for a differential change. So here I can, if I divide this one by dt and this one by dt, what I'm going to get, I will get S dot, which is equals to rho theta dot. So now I can say that theta dot is equal to S dot over rho. And then I can say that ut dot is equal to S dot over rho multiplied by un. And there I am getting rid of theta dot. But what is S dot? S dot is v. The rate of change of position is velocity. So what I'm going to get actually is that this is v over rho un. So from the previous relation, if you remember, what we got was that the acceleration is equal to v dot ut plus v multiplied by ut dot. And now if I substitute this in here, what I will get v dot ut plus v multiplied by v over rho un vector, which is indeed the famous equation v dot ut plus v square over rho un. To summarize this, we have now found that the acceleration vector is v dot ut plus v square over rho un. And this is what we call AT, the tangential acceleration, ut plus the normal acceleration un. So the tangential acceleration at is v dot, the rate of change of the velocity, while the normal acceleration is v squared over rho. Therefore, the magnitude of the acceleration is basically the square root of at squared plus an squared. By this, we end part 1, and you can watch the remaining part of section 12.7 in part 2.